to thank the organizers for making this possible, despite the circumstances. So let's hope the bandwidth will be fine and the audio is okay. Otherwise, I'm sure you guys will let me know. So in this presentation, we are going to to talk about 3D printing, of course, and more specifically to discuss about what happens or what does not happen in your 3D prints. And what I mean by does not happen is because sometimes you simply want to print as empty as possible, and this is something we will look into more details later on. This presentation will have a strong bias towards extrusion systems. You probably are all familiar with filament-based printers, where we push a filament through a hot end, the filament melts, and then you're depositing layers of molten plastics that solidifies immediately. And the reason we are very interested in these printers is because they are widely available and inexpensive. They are very easy to hack, which means you have a lot of room for experimenting new ideas and new things. But also you have a great freedom in terms of the materials you choose, the way you can deposit the filament, and so on and so forth. And this makes it very interesting to address. This doesn't mean that what I will present only applies to these technologies. There are things that, of course, go beyond this particular additive process. And I will try to give you some insights about this. All right, so why would you worry about how you feel the interior of a part? Well, in fact, most of the physical properties of an object are directly influenced by the way you create the interior of this particular object. For instance, the weight of the object, its balance, will it be robust? Will it be robust to fracture? How will it sustain fatigue over time? But also, of course, its rigidity or if flexibility will be directly impacted by this. The other thing that the way you infill the volume impacts is how long it will take to fabricate your particular object and how much material it will use. And this strongly depends on the technology, of course. But for extrusion systems, usually the time it relates strongly to the amount of material you are using because you're extruding this material, so it has to go through the hot end to produce the final print. And so 3D printing gives a lot of freedom in the way you can create the inside or the way you can infill the internal volumes of your objects. And the reason is because we're adding material progressively, slice by slice or layer by layer. And so you can really create very intricate and complex structures. Here I'm giving some examples which are actually printed on a selective laser sintering. These are industrial machines that are sintering powder in a bed of powder. So they can create this kind of very complex structures here. So additive manufacturing gives you a lot of freedom, but you don't have complete freedom either. There are a number of geometric constraints you have to worry about, and this is actually what makes the problem very interesting. So let's have a look at some of these constraints. The first one that is not to be underlooked is the fact that you have a given solidification width on your machine. Typically on a filament printer, this is going to be the width of the bead of molten plastics that you are depositing. And this means that any feature that is thinner than this particular solidification width will either have to be deleted, it will not print, or it will have to be thickened so that you can actually reproduce it properly. So that means that all the features like the pointy tips, but also the thin part inside may not print properly, which means you will even possibly change the topology of the object you want to create. Another constraint is the fact that because you are printing layer by layer, and here we're looking at the print from the side, if in a layer something appears, like this purple region here, something appears that is not supported from below, with many technologies this will be a problem. Like if you're extruding material, the material will just fall because there's nothing below to catch it, and in which case you will require some external support structures. Some technologies are a bit nicer in this respect, like if you have a bed of unfused powder, the powder itself will support the part, but still you might have some issues requiring to add similar support structures. Now, another issue which is related but not exactly the same is the overhang limits. So if you have a slice, it will support more than its actual area on the slice above. So you can go a little bit further away than the slice below, but if you go too far, things will start falling again, and you have to worry about this. So this gives a maximum overhang angle constraint, which is usually lower than the vertical, typically 45 degrees, but you have to not exceed this limit to get the best possible quality. And finally, and this is very important when it comes to creating things inside parts, some technologies can create pockets. What I mean by a pocket is an enclosed void inside your print. So with some technologies like filament, it's going to be acceptable. With some others, you simply cannot do it, because if you do that, you will trap uncured or unfused material inside the part. And that's bad because, of course, if you want a lightweight part, it defeats the purpose, but also it's quite bad if you leave uncured material inside. If the part is broken, it will exit, and this will not be good for the final user. All right, so these are geometric constraints shared by many processes, and then you have some constraints which are more specific to the particular type of technology you are targeting. So for instance, with extrusion-based system, you have to worry about underfill and overfill. So underfill will happen because, for instance, you have this very sharp turn here in your trajectory, and you can't possibly reach the pointy tip here that is created by the two other deposited beads. And this will leave a gap that might make your part porous, or might be a place where a fracture will trigger later on. Overfill happens, and here this is quite a severe overfill, because two trajectories come too close to each other, and then you will put material twice at the same location. So if you do it in a few places, it's sort of okay, because the material you're depositing is not yet solidified. So it will go around, and that might be fine. But if you keep accumulating overfill in the same place or throughout the same location, or throughout the slices, it will endanger the feasibility of your print, and you might and this might lead to catastrophic failures. Now, the other issue, which is difficult with extrusion-based system, is that because you are pushing material through a nozzle, you are building up pressure in this nozzle. And when you want to stop extruding material, because, for instance, you're done printing some region of a slice and you want to move to another region, you have to stop the extrusion, you need to release pressure inside the nozzle. And for instance, with a filament printer, what will happen is that we will retract the filament back into the feeder, and this means we will have many rotations in both directions of the gear that is pulling the filament. If you do too much of that, you will grind through the filament, and this will lead to issues such as missing plastic or even complete print failures. So of course, the systems are optimized to support this, but you should be careful to not do it too often. Otherwise, you will have problems with your print. Now, the other issue is transfer moves, and this is particularly a problem if you're using flexible filament or if you're extruding clay or ceramics. What happens here is that you are printing a continuous feature, and then when you stop printing because you're done with this particular feature, you have to do a travel motion where you're not extruding anything, and usually you want to do this quickly. When you do that, if the material is very viscous, it will be carried by the head, and this will damage what you just printed. And if you do a lot of those transfer moves, this can really be problematic in the end. So why does it matter? Well, here is an example. If you look at infill structures, there's a lot of excellent work regarding infill based on trusses, on truss networks, for systems which are using powders or resins, that is selective laser sintering or stereolithographic systems, because trusses print very well on such systems. But the problem is, if you want to do this on an extrusion-based system, what will happen is that whenever you slice a truss network, you will get a lot of tiny disconnected regions. And this will translate into a lot of start-stop of the extrusion process and a lot of transfer moves, leading to really bad quality of the print. So it is possible to do it, but you won't get the nice mechanical properties you would have expected. And it will also mean that a few beams are going to fail, and you will run into problems. Whereas these techniques work extremely well on stereolithography and selective laser sintering. So this means that a good infill technique for the inside of your part is a careful balance between several factors. The first factor is reaching your desired physical property, minimizing weight, maximizing rigidity, being flexible in some areas. The second factor is, will it be reliable to print, and will it be fast to print? Because of course you're filling a volume, and the size of the volume grows to the cube of the scale of the part. So you really have to worry about how long it takes to print. And the final thing is, how efficient will this be to compute? Again, we're filling a volume, and so memory can quickly be a concern. We're talking about generating features that are in the scale of tens of microns, in parts that are in the scale of tens of centimeters, possibly a meter. And so this can really lead to computational issues. Memory is a problem. Time can be a problem, because in our field, designers and engineers, they really like to be able to look at the trajectories and understand what will happen in the part. especially if you're creating complex structures inside with grading of properties and so on. And so if your technique takes hours to compute, it will slow down this iterative design process. Now, the good news for us researchers is that this means there is probably no best forward approach, which means there's a lot of space to explore and to come up with novel techniques and to try to apply different trade-offs when we look at these infills. Okay, so to understand this from a practical standpoint, I would like to show you a little bit how the infills evolved for filament-based printers. So maybe 10 years ago, most of the infills were created with line patterns that were created in a slice and repeated vertically at every slice, which means you would actually create vertically extruded walls from this line pattern. So for instance, in a slice, you would create these red lines, and this would repeat every slice, creating vertical walls. Now, the pattern you obtain from this would actually be mechanically not great, because of course, if you press on the side, it would collapse, and it also has a very strong directional bias due to the planes you're creating inside. So what's possible is to add a second set of lines. These are these green lines that will cross the first one. And this will make the pattern a little bit nicer in X and Y, but you still have this problem that this would be very susceptible to shearing in the XY plane. Now, you might wonder, because here I'm crossing two sets of lines, and so I will create overfill when this crosses. This is considered okay on extrusion systems, especially as what we do is when you do one direction on the slice, you change the direction on the next slice so that you will avoid accumulating any defect throughout the entire print. So how could you improve over this without making something too complex? Well, a simple idea is to add another set of lines, and then as you move up the slices, you start offsetting these lines just a little bit. And as you do that, as you go up the slices, you're actually creating a set of walls which are no longer vertical, they are now slanted walls. Of course, you have to worry about the overhang constraints, so they're still within the overhang constraints, and this creates this kind of 3D structure. And this one is much better, mechanically speaking, because this is actually a known structure in material science, which is known to have a nice bulk modulus and reasonable properties when it comes to shear and so on. The advantage of this is that by a very small change in the way we were generating the usual pattern, just adding these offsets to the lines and this other set of lines, now we're creating a nice 3D structure. And I think this is a good example of how you can play with these trade-offs. This is fast to print because they're just a set of lines, very trivial to compute and yet quite rigid and interesting. What's more is that because this is actually a grid which is rotated on one of its corners, right? If you look at this, I think you can recognize the grid. We can actually subdivide it, which means we can now do things such as density control. So you can paint inside your model a field that will tell I want this density at this location, and then we will subdivide the grid according to this. This is a screenshot of our software where you have this kind of painting tools available. So, of course, since the past 10 years, a lot of interest has been, the interest has been renewed for extrusion systems regarding this kind of infills. And I want to mention two works that I think are quite representative of the type of things that have been done. So the first one is work by Wu and colleagues, where they combine this type of infills for extrusion systems with an optimization that can do things such as optimize the part for rigidity or optimize the part for balance. What's really good here is that this is optimizing using the infill itself as a design variable. So it's truly integrated with the fabrication process. Now, some recent work by Kuipers and colleague has been looking into using space filling curves to generate 3D infills. So the idea, so why is it good? Because the space filling curve is actually a continuous path, which means you will never stop the extrusion process, which will give very nice properties. Also, if you're very careful in the way you construct it, you can completely avoid overfills. And they found this way to create this nice 3D interpretation of the pattern, which will create these collapsible structures so that you can control flexibility throughout your part. So here's a reminder of the keynote. First, I will describe to you some of the other techniques we came up with to generate light and flexible infills. And then in the second part, I will detail some ideas to be able to print very large objects. And when you do that, you really have to worry about the amount of material you put inside the volume, which means you want to actually print as empty as possible. And of course, I will conclude by showing you some recent work that I think is quite promising as future research directions. Okay, so when you do these infill structures, if you look at the infill at a sufficiently large scale, this infill actually becomes equivalent in terms of its average mechanical behavior to an equivalent homogeneous material. And that means that by playing with the infill, you can actually give different properties to the part than the properties of the material you are printing with. What's more is that many of these infills, they actually have parameters. So for instance, the one I'm showing at the bottom, you can change the density of the bars inside the structure, and this will actually change how rigid or flexible the final part becomes, which means you are introducing a parameter in this equivalent homogeneous materials that you can control throughout space. And this is a very powerful concept because you can do things, as I will show you, where you will be able to modify the behavior of the part. So here is an example of one of these equivalent material space. What you see on the right here is a graph where every entry, every point of this graph actually corresponds to a structure that is being created by one of these infilling algorithms. And what the graph is showing is how stiff or how flexible the sample is along the x-axis and the y-axis. And so for different points in space, you get different structures with different properties. And the last one I'm showing here, you can see that it's actually much stiffer in the x direction and much more flexible in the y direction. These type of materials are called orthotropic, and having the ability to design such a material throughout your part leads to very interesting possibilities. For instance, you can do things such as this plate here, where if you bend the plate in one direction, it will create this C shape, as would a homogeneous material plate do. But if you bend it in the other direction, then it will create folds at two specific locations and will lead to this U-shaped parts that you have at the top right. You can also use that in a volume, for instance, to design this kind of chairs, where hopefully this would be comfortable when you sit on it, but it won't collapse because the overall structure is done in such a way that it will maintain its rigidity. All right, so it's very important to be able to grade this parameter through space as you do this kind of structures. Now, if I want to do that for an extrusion system, I have to worry about the constraints I was mentioning before. And for extrusion systems, the main constraints are this notion of being supported from below. We call that the non-local minimum because you can consider that this particular purple piece here is a local minima in the shape as seen from the printing direction. The other thing you have to worry about are the overhang angle constraints. And finally, as I said before, you want to avoid having tiny regions in a slice. So when you look at these constraints and think about what would be a nice infill structure for an extrusion-based system, one structure that comes to mind and that is well known in the material science literature is to use a Voronoi closed cell foam. So what this is simply the Voronoi diagram of a random set of points, and you take the faces of this diagram and you give them some thickness and you 3D print this to obtain the infill structure. So what's good is that it's very efficient to compute such Voronoi diagrams. I'm citing here one of the many possible approaches to do that. And when you slice this diagram, because you're looking at the faces, you will get a set of lines or a thick lines in your final slice. So that's good for extrusion systems. Now, because all cells are convex, you also have resolved the problem of support because everything will have something below and you will be good from this point of view. However, there is one last issue, which will be the main problem with that idea, which is the overhang constraints. Because in general, if you take the faces of a Voronoi diagram, they will take any arbitrary orientation in the diagram, which means they will violate the overhang constraint. So let's have a look at this a bit more closely. Here I'm looking at a 2D version of this Voronoi diagram. So we have edges instead of faces, and the print direction is given by this arrow. So everything that is red here is violating the overhang constraint and will not print properly. So what can we do to fix that? The thing is, this Voronoi diagram I was showing you is computed with the usual Euclidean distance, which I can represent by this circle. This is the points which are at a unique distance from the point in the center. And this creates this problem that the faces will take any arbitrary orientation. Now, a very interesting observation that was made by my colleagues Jonas Martinez and Samuel Ornus is that if you change the distance, for instance, using the L infinity distance, you still obtain a diagram which is not okay for fabrication because it has many flat faces. However, the number of orientations that the faces can take is now finite. And this means that based on the distance, you will change the amount of possible configurations within your Voronoi diagram. And this is actually a known property of distances. And the question is, what distances could you use that would give you all the right properties? And it turns out that in 2D, you could use a triangular polyhedral distance. And when you do that, you actually get something where everything is supported and everything is within the overhang constraint. And this can be proved by enumeration of all the possible configurations. All right, so let's have a look at what happens in 3D. So here you can see the different Voronoi diagrams that are obtained using different cone distances. And what's nice about it is that by changing the shape of the distance, you can actually create a bias in the orientation of the structure, and this will translate to this orthotropic behavior I was mentioning before that we can exploit within the prints. What's more is that we can show that if you grade the distance spatially, because you can change the distance that is being used between pairs of points throughout space, when you do that, you still maintain this nice property that everything will be below the constraints everywhere. And with that, you can produce parts such as this one. So here we've plugged the diagram generation inside an interface where you can paint some fields to control the densities, the orientation of the features, and so on. And this creates parts such as this shoe insole illustration here, which is more rigid in these parts, more flexible in these other parts, and that will bend in the way we want because we have triggered orthotropy in this particular region. All right, so one point that I think is worth mentioning, even though it's perhaps more of an implementation detail, is how do we actually synthesize these things, right? Because like I said, you can easily run out of memory when you try to generate such diagrams. What's more is that, as far as I know, there is no 3D polygonal implementation of polyhedral Voronoi diagrams that are available. And so we actually do it in a discrete manner. So what we do is we generate images of the slices. These are, of course, high-resolution images that are generated on the GPU, and we use a pixel shader to determine for every pixel to which cell it belongs. And we output the ID of the cell. Here it's color-coded for visualization. Once you have that, you can write a very efficient algorithm that will extract the tool paths as the boundaries of this cellular map to get the final tool path. And what's nice about this way of approaching it is that you are generating the trajectories directly, which means you will have exactly the thickness of your deposition process, as opposed to have to generate, let's say, a mesh or a thickened mesh of this Voronoi diagram, which would be extremely difficult. So this is actually something that is available in our software. It's called infill shaders. We have example code, so if you want to do research in this, I encourage you to try it out. It's a very nice way to write your own infill structures and to experiment and play with it. And you can also directly pull from the density fields that are painted by the user in the interface. All right, so what's good about this structure I just described is that it gives you a lot of freedom in terms of the material space you can explore with orthotropy and variations of density and so on. However, they are also very irregular. So when you print a particular slice of this material, it's taking longer than your usual infill because it has lots of sharp turns and so on and so forth. And so the question is, what could we do to improve over this? And to try to make things better, we actually went back to this initial idea I described you about how to combine 3 sets of lines to create these cellular structures. And it turns out that when you do this, these lines don't have to be straight lines. You can actually curve them, or you can actually also use a pattern of splitting lines. And so if you are given a scale field that would drive density and a parameter field that will tell you what direction should your lines have in space, then the question is, how do you generate a line pattern which is evenly spaced following the scale field and going in the chosen orientation? And of course, this problem strongly relates to a streamlining problem, which are long-standing problems in our fields. And so we proposed a new approach to do that efficiently from a procedural shader. This is an upcoming paper at I3 2012. It's already available. We have code online. And this is actually something we have already in our software since maybe like 3 years or something. And we can create the patterns you see here at the top. And I have one example here that is physically printed. And I will show you a little bit later why this is good mechanically speaking. But the thing is, this is much more regular than the polyphone patterns, and so it's much nicer to print from an extrusion point of view, much faster, I should say, to print from an extrusion point of view. All right, and here's a comparison between the three ideas. So the first one we discussed was the cubic subdivision pattern. The main issue with this one is that in terms of mechanical properties, you have actually abrupt jumps in density, because when you subdivide, you have no in-between, right? So you have to quantize your density field in a manner that will make the density jump abruptly here. And this means that when I bend this thing, you can see there is a mechanical frontier here. Also, it has T-junctions, but many of the other patterns do as well. So this one, which is much more regular and fast to print, is much nicer in terms of mechanical properties, because it will bend nicely, because it approximates well the density gradient that the designer wanted. And the polyfoam will give you the greater freedom in terms of material properties and in terms of what you can do within a part. But unfortunately, it has this problem that it will take longer to print. Just to show you, this hand is actually filled with a polyfoam, and it will make the fingers flex nicely thanks to the way the foam is inside. It's also more flexible here, more rigid here, and so on. It's a bit hard to, you have to touch it to really understand this, but this is quite nice that you can do this on a printer, which costs only a few hundreds of dollars with a very inexpensive flexible filament. All right. So now we're gonna switch to a slightly different topic, which is still very related, which is how can we print large parts? I mean, if you have operated a filament printer in particular, you know that if you go above like 10 to 20 centimeters, then it's really starting to take a significant amount of time. And the reason, of course, is that the volume grows to the cube of the scale of the shape, but also you have to put some infill inside, because if you don't put enough infill inside, your object will simply collapse, in particular the roofs of the object. So one intriguing question that came up in the community is, what would it mean to maximally carve the inside of a volume? And here is such a cavity here that would print properly, because it enforces overhang angles everywhere. So how big is inside your part while still printing properly? The hope here is that, because of course we have support structures, right, for the outside of a print. So you could say, okay, I'm just going to print the, some hull around this part, and then I will grow external supports simply inside the print. But the hope here is that because we don't need to remove the supports because they're inside, we can maybe do better and do things a bit differently, thanks to the fact that the supports don't have to be fragile. We don't have to worry about how they will be removed later. All right, so to understand these techniques, we need to look a little bit closer at what it means to be printable. So here we're looking at a cross-section of a number of beads which have been deposited orthogonally to the screen, right? And the up direction is the printing direction. So the bead that is at the bottom, of course, will print fine because it's laying on the bed. The one just above has been offset a little bit, and this will still print fine. The reason is that there is enough bonding between this particular bead and the bead that is below, so it will be properly supported. The one above is starting to be offset by quite a large amount. It's half its width. This actually is still considered as printing okay, and if you do it experimentally, this will usually still give you a good printing quality. Of course, if you push it further, this will no longer work, and in particular, these beads here will simply fall if you try to print them. And this is actually where the overhang angles comes from. This gives you, under most typical setups, the 45-degree overhang constraint. You can observe that if you print thinner, this actually this slope will decrease, allowing you to print more and more overhang, and this is verified experimentally as well. Now, what's true as seen from the side is also true when you look at this from above. So for instance, if you have deposited this bead and you look at it from above, at the slice above, it will be able to support an area that is larger than itself, right? Thanks to this notion of you can offset the beads a little bit above. And this is an important notion that is used by most of the techniques I'm going to describe. Okay, so how can you do a maximal printable cavity? Actually, that's a problem that has received quite some interest in the past years. And again, I will cite here 3 works that I think are quite representative of the types of techniques that have been created. So the first one is actually starting from one of these rhombic infills, and is removing all the walls that are not strictly necessary for support. Because here, I should precise that when we do that, we are no longer interested in the mechanical property of the part, right? We are interested in printing fast, large objects that are going to stand on a shelf, right? So in this discussion, we're really assuming that, mechanically speaking, this will be fine, even though we print with as few material as possible. That's open to discussion, of course. So here, you're removing everything that is not strictly necessary for support, and you're generating a larger cavity inside. The second work is actually a different idea, where you are trying to pack holes, voids, with a specific shape inside the part, and you try to pack many of these voids, and the voids are designed so that they will be nice to print. In particular, they will be self-supporting when you reach the top of the voids, and also they will, in this case, generate nice circles that are better to print with an extrusion system. And finally, the last work here is generating empty pockets inside the print and then formulating an optimization problem so that the pocket will inflate as much as possible to take as much space as possible while always being printable. And so this leads to very significant savings. In particular, the model that is shown here is only using 25% of the total volume. That's including, of course, the outer hull. So that's a very significant reduction of the volume. So now the question and the work we did in this space was really to try to go larger scale, right? So, and to go larger scale, the challenge you have is really that you can't invest a lot of computational time, because if you formulate an optimization here, you have to face the fact that it will also scale to the cube as the volume. So we wanted to do something that would be very simple algorithms, and hopefully algorithms that can simply sweep through the slices and still generate something reasonable in terms of material saving. And so here is one of these approaches that we looked into. So the idea is to start from the model, which is fully sliced. So here we're looking at the model from the side, and all the slices have been generated, and we're assuming the slices are fully solid. What the algorithm will do is it will sweep through the slices from the top to the bottom, and it will start by punching a little hole at the slice at the top. Of course, this hole, because this is a 2D slice, is actually a skeleton in the slice. Think of it as a medial axis skeleton. And so now what we are going to do is, as we go down through the slices, we will grow this hole as much as possible under the overhang constraints. So this hole is being inflated as much as possible, and this is done through simple morphological dilation of the cavity area, or through erosion of the complement, which is the slice with the hole, right? And so you grow this region, and then what happens is that you're left with this large printable cavity inside, but of course you have these two big chunks on the side, and then you can iterate the algorithm inside each of these volumes, and which will create the nested pockets that we have seen in prior techniques as well, right? And so here, of course, this is a medial axis, which is in what remains of the slice, and we grow it downwards to obtain the final result. And what you actually print are the frontiers, the boundaries between these cavities, or the walls of the cavities. Here is an example in the Kitten model. And here we're really pushing this idea quite far, because we are only printing the outside of the model with a single bead. Of course, we're assuming the model is self-supporting on the outside, because we consider this an orthogonal problem. For the outside, you would use any other support technique to do it. All right, and so with that, you can print fairly large models. Here is the Kitten, which I believe here is like 30 centimeters tall. I'm not completely sure. But the print time was 49 hours with a reasonable setting, without doing anything special inside. And using this technique, we reduce the print time to 12 hours. And you can also see that we reduce the amount of filament by 5. The reason we count filament in meters is because we are counting we are measuring how much we unroll the roll of filament that comes with a printer. A specific roll typically has 300 meters of filament. And so, for instance, in this, for this particular model, the model without our technique, you would not be able to print it with a single roll. You would have to put another roll of filament, or use a bigger, less common roll of filament to be able to do it, whereas with our technique, you can fit multiple of these models on a single roll. All right. So the good thing as well is that these techniques, they scale fairly well with the size of the model. So if you look at the graph at the bottom right, this is showing the amount of extruded material versus the volume of the model. And it turns out that it's not strictly quadratic, but it grows more like a surface as opposed to as a volume. And the processing time is also quite well behaved as we grow in size, because this is, again, just a simple sweep through the slices from top to bottom. Now, this technique, unfortunately, has some quite severe problems, and there are two of them. The first one is that it will produce local minima. And if you have seen the keynote by Xiaoping Qian 2 days ago, you have seen that there was a very similar problem, because if you only consider the angles during the optimization, you will end up with these local minima. They have to be treated separately. In our case, we can't really treat them. The only thing we can do is put some bridges after the fact. And so here, for instance, we have to add this bridge structure. So they are not defects, they're here on purpose to support the local minimas above. That works okay, but as you increase the scale of the object, this starts to be a bit fragile, and this can lead to problems. By the way, a very nice observation in the work by Wang et al. Is that you can decompose the model into chunks which are topologically simpler ahead of time, and I believe this would be a nice way to avoid this issue entirely. All right, the second issue that we have is that because we are using morphological operations, there are things that the algorithm does not see. And in particular, if you have a thin strip in a slice, when you do the erosion, this entire strip might disappear and will not be further supported from below. That can lead to problems in some models. The models where this happens are not very common, but this can happen, right? So it's not very satisfactory. Okay, so now I'm going to describe some work by colleagues of mine, Frédéric Clos and Thibaut Tricard, who came up with this completely different take on this problem. So their idea was no longer to think about the cavity, but again to go back to generating supports inside the empty parts of the model. But the idea here is because these are supports you are not going to remove, you can do things a bit differently and hopefully come up with a technique that still saves a lot of material, but will not suffer from the problems I mentioned before. So here is the idea. We're going to describe it on this simple cube that is on the left. And of course, the last slice of the cube is fully filled. And we are starting from the top, looking at the slice before the last, okay? So the first step of the algorithm is quite typical. This is done also for external supports. We will select a set of points in this slice. In this case, this is going to be a Poisson-Dietz distribution of points. And the idea is that these are the points you really want in the support structure because they will be responsible for supporting what is above. And each of these points is supporting a larger radius around them. Here, of course, I'm exaggerating. And if you take the union of all the points, they should support the entire slice above. Now, if you want to print this on an extrusion-based system, this is not going to be nice because you have tiny regions and so on and so forth. We have seen that before. So instead of doing that, their idea is to create segments in the slice that will connect each of these points to something that has been already printed. And because we're inside a part, we have something that is already printed, and that is the enclosing wall, the outer wall of the print that we often call the perimeter. And so here what will happen is that we will take the points from the closest to the furthest from what has been printed before, and we will connect them through segments to these previously existing structures. And as we do that, we add the segments to the existing structure so that they are taken into account by the points which are considered later. This means this will quickly create a hierarchical structure which looks like a tree. And so what happens here is we have spent a little bit more material to make this nice to print, because this material we added is not strictly necessary for support, but it is necessary to ensure that we have a nice deposition process. So now when you go to the next slide, things become very interesting, because to support this tree from below, you can simply use another tree, which is the same tree, but it has been retracted a little bit because it doesn't need to extend to the same endpoints, thanks to this fact that something below will support something larger above. And here I have overlaid both trees in the slice in the middle, and you can see that the blue tree is ending earlier than the white tree. So what happens is as you go down, these trees are retracting within the outer walls and quickly vanish from the print entirely. All right, so let's look at 3 slices from an actual result. This is for a cube. They are not consecutive slices. There are, I believe, 10 or 20 slices apart. What happens as well, as you look at the slices, you can notice that the trees on the right become simpler in the sense that they are less curved and straighter than the trees that you had in the middle. And the reason for that is we exploit the fact that when you have a bead in a slice, it actually can support more above, which means it can support something that is curved above. So you can straighten these segments, which leads to, of course, shorter trees, but also even faster deposition. All right, and here you can see the technique in action. I have actually one of these models, so you can see it's actually a fairly big, cute Octo says hello model, which you probably know if you have a filament printer. And you can see the structures that are being created inside the part. So there are wall-like structures which are creating these vaults inside the part. I won't detail this table, but it's just to show you that it's on par or slightly better than the previous technique as described, but it has the big advantage that you no longer have to suffer from these local minima, you no longer have to worry about missing features as long as you select these points carefully, and it's still very fast and efficient to generate. One drawback, though, is that you are creating some tiny segments, so you have to be a bit careful in the way you order them and the way you create your travel moves throughout this. So it's a bit more complex in this respect than the ones I showed before, which are just cyclic paths for the most part. All right, so it's time to conclude. I think I'm still doing okay on time. So to conclude, I just wanted to mention two ongoing areas of work which I think are quite interesting to look at, and if you want to invest some research in this domain, I think these are good starting points. So the first one relates to the extrusion of paste, and to try to have as continuous as possible infills. I've shown some examples of that before. Here at the bottom is an example of work we did last year to print clay, which is a very difficult material to deposit because it's very subject to transfer moves. And actually this year at SPM, there were two papers related to these particular problems that I highly encourage you to read and to see the talk if you have the opportunity. Another problem which I think is very interesting, there's been work in the past about this particular issue, but it has renewed interest these days, is this notion that sometimes you don't want to print sparse, as I showed, sometimes you want to print as dense as possible. And when you want to do this, the game is to leave as few porosities as possible while not creating overfill in your parts. And so there's been some recent work on this particular problem, which I think is quite interesting to look at in the future. Okay, thank you very much. I'm happy to answer questions. I saw some things popping up here in the chat, but I couldn't look at it yet. Thank you very much. I hope you found the presentation interesting, and I put some links here if you want to go deeper into our work. Of course, I would like to thank all the colleagues with whom I did this work. This is the work of several students and colleagues in the team, as well as external collaborators. And I encourage you to try out our software. It's, of course, free to download. It even has an online version. So please go ahead and let us know what you think. Thank you very much.
Okay, so I think we have a few questions shown in the chat board.
Okay, sounds good. So let me just adjust my setup a little bit.
Yeah, if you
do
not go through the screen, the full screen mode, you probably will see it, or I can read it for you.
Okay, sounds good. So I stopped sharing for now. I will bring it up again if we have slides to show. And let me play a bit with interface. Oh, for some reason, I cannot see the chat anymore.
Okay, there's
oh, no, there it is. There it is. Okay, sorry. No, I can see it. Okay.
I can also just read the question and pose it myself.
Sure. Mm-hmm.
So,
please.
Yeah, you had a couple of slides on methods for cavity-based infill reduction, which were based on reducing the inside material by introducing voids. But I think there are quite a lot of support algorithms out there, which if you just apply them to the inside, so you just reduce all of the material inside and then just use normal support algorithms for those regions, that I think use a lot less material. So what is the advantage of these cavity-based methods over support-based methods?
Right, so that's a very good point. So the first thing to keep in mind here is that, so first, it's not easy to compare this. We actually tried to do these comparisons by using external supports inside a print. The problem is many of these techniques are actually optimized to avoid the walls inside. And so it's a bit tricky to exactly know what will happen if you allow them to attach to the inner sides of a part. I would say the better reason you maybe don't want to do that is that these techniques are optimized so that the supports are fragile and easy to remove. And for this reason, you always end up, in my experience, with some structures which will take a bit longer to print and will be a bit more tricky to print because they're just at the edge of what can be safely printed, right? So that they're easy to remove, right? So I think that's one reason these inner cavities are a bit different from the external supports. But clearly, there is an in-between, right? So there is a link between both. These external supports, these internal supports, sorry, you could also try outside. It also makes sense for some of them. And so I think it's not like a clear-cut separation between both. You are correct.
Right, thank you. I think there's also another question in the chat.
I think the second question is mainly about creating cavities inside the model with changing the balance of the model.
Right. So very good point. So in particular, this is a big advantage of the optimization-based techniques. I mentioned one of them in one of the slides, which is work by Wang et al. I think, Charlie, you were involved in this one, right?
Yeah, right.
Exactly. And so this one has this big advantage that because this is an optimization that is being formulated, you can have secondary objectives. And that's great because indeed, you can then take into account the balance of the objects. Our algorithms are completely blind to that. And that's one of their drawbacks is, again, they're completely, they're ignoring entirely the mechanical issues. And in some cases, this is not what you want for sure.
And then the third question is about, is the polyform Voronoi form also relevant to the powder sintering?
Right, so I wish it would be, but the problem is if you create a closed cell structure, you're trapping the powder inside. And this is usually, well, I mean, in terms of mechanical properties, of course, it's a significant change of what you will get at the end. But what's more is that usually it's considered as not being acceptable to trap infused powder inside the prints. So I would say this is probably a no-go for these technologies, unfortunately.
Okay. And then the following question is about, is it possible to control the porosity when infilling is done? And for example, is it possible to replicate the bones?
Right, so this is a very good question. It's one of the motivations is to replicate bone-like structures, in particular trabecular structures, which can also become orthotropic. So yes, you can control the size of the properties by controlling the density. In our techniques, you would have to paint these fields yourself, but then there are great works, for instance, the work of Junwoo from TU Delft, with optimizing through topology optimization for porous structures by adding a term in the optimization that controls the porosity. So yes, this is a very important objective, of course, for medical applications in the long run, but also for mechanical engineering. And yes, these types of controls, that's one reason we do orthotropy and we do density control, is to be able to control the size of the porosities inside and their orientations.
And
bridging. Yeah, so I see a question about, in Voronoi diagrams, you can mitigate some problems by using bridging. Yes, so bridging is a very nice capability of filament printers. For instance, this is something we have used to design support structures because you can save a lot of materials and avoid a lot of supports by using the bridges. I would say the problem when it comes to infills, especially if you're after some mechanical properties, is that it's very hard to be confident about what happens exactly on these bridges, right? So I'm not saying this would not work. I'm just saying that you will really have to look carefully at what happens to these flat surfaces. So maybe that's an option. I mean, definitely it's possible to print them properly if you're a bit careful with the setup of your printer. The market size. So there's another question about the market size of the different printing approaches. I'm not sure I know how to answer this. I mean, so my experience is that in the industry, the most common seems to be selective laser sintering and stereolithography. I think Charlie, you can probably answer this better than me. But and then in school, makers, enthusiasts, research labs, filament printers are great either for prototyping, but also for experimenting with other types of materials and depositions. What would be your take on that, Charlie?
I think for extrusion based, if you are focused on plastic, there are some options you can print at a size of about a ½ meter by ½ meter by 1 meter this size. There are quite a few companies working on this.
That's true.
And then that's the largest. And if you go to the smallest size, I think it's about micron level. They're able to do that. And then that's probably at the 100 nanometer level. This is also possible, but I didn't see anyone who's really commercialized for the tens of nanometer scale. I didn't see that.
Yeah. Now, can you hear me?
Yes.
Yes. Mm-hmm.
Yeah. So Andreas Fabri, my name. So I asked this question about the market size. The question is, you said the extrusion-based systems are easily available, so that makes it interesting. And my question is, the market. How many commercial users in the world use this kind of approach? And so in a, well, if I wanted to be negative, I would say how relevant or irrelevant is it to do results on extrusion?
Fair enough. Yeah. No, I see your question. So I really don't have the answer in terms of market space. It's a bit hard to answer. I think the hope, however, is that there are specific things you can do with these printers, even though they're inexpensive. For instance, closed cell structures, and using these specific materials or using multiple materials within a part because you have several nozzles are really specific to these technologies. So, in fact, what I'm saying is that I believe you can go further with this particular extrusion-based technologies, not only filaments, but them in general, than we can go with other technologies. And you can explore things which are different from them, right? So it's not necessarily opposing them. It's more like they are in different spaces for some of these methodologies. And again, many of the things, however, are shared by different techniques. And so a lot of the methodologies apply in different on different technologies.
And extrusion, it will also work on other materials, right? I mean, there are things like glass or...
There are things like metal, there are things exactly. Because for instance, there's this flat process that will, or this wire arc welding process where you will basically deposit a bead of molten metal. So there are other processes, right, with different materials. So I think it can be relevant to a wider range beyond just filaments. Yeah.
No, but I mean, it will be also filaments with other materials than plastic, right? But it will stay filament and filament. So solutions for filament printing will carry over to other materials, I guess.
Some of them. It's never obvious, right? It's never obvious.
Okay. Thank you.
Thank you. So.
I think there's a question about speed.
Right, sorry, I'm having a hard time following all the questions. So maybe, Charlie, you can select the next one.
Okay, I think there's questions like if the user wants to print a model as fast as possible, what will be your suggestions?
Right, so if you want to print as fast as possible while keeping some, like surface quality, which is what you would traditionally get, I would advise trying one of those cavity techniques, right? Of course, I'm going to say you should download our software and try it out. We have the cavity one inside. We don't have the second one yet implemented, but I'm sure there are other potential softwares available. Now, if you want to go even faster, there are actually other techniques that I did not mention, which are doing previews of parts. And in particular, there are a number of techniques which are printing filament and waiting for it to solidify so that they can print a truss structure in paste and give you a rough outline. So depending on what you want, this is worth considering. Oh, of course, you should also increase the size of your nozzle and print thicker layers, right? That's also a way to get a faster rough print. Also adaptive layering. I mean, there's many aspects to this, right?
And Michael asked a question, and what are the pros and cons about 5-axis additive manufacturing? As far as I,
Right, sorry, so exactly, so the techniques we presented are 3-axis. I mean, they should work on 5-axis, it's just that they would not exploit the nice fact that with 5-axis you can orient things, so you can go away with some support. No, I think 5-axis AM is great. Actually, that's something we're also looking into. We have done work with Charlie exactly about this. And I think it's greatly promising for the future. The main issue is you need a 5-axis printer, which is quite something else. And 5-axis, because you can locally orient the part, you can indeed go away with a lot of the supports. Not all of them due to accessibility concerns, right? So there are parts of the print you may no longer be able to access, and you will still require some sort of support in such cases. All right. So I think, Tim, if I correctly understand your point, you're saying that if we would like to remove the walls to be even more flexible, then you would need some internal supports to the structure, right? Is that correct?
Not really. So the thing I've noticed is when I print some model with a foam on the inside, then generally in FDM you still print the outside, you still print the shell, and the shell makes it it just
yes.
kind of counteracts all of the properties of the foam, because the shell is so much more rigid than the foam on the inside. So if you want to print with these foams, you have to do without the shell. And if you print objects without a shell, which has maybe some overhang, like, okay, I'll get something here. So then the foam in these areas will create overhangs which are larger than this angle, because the foam itself also has angles. So what does that mean for support generation, or what does that mean for the design space of models that are printable, or how should we deal with that?
So that's a very good point. So it is absolutely true that the skin is going to change what you obtain in your model. That being said, on parts like this, you can still get fairly flexible, and you can do some quite some bending even though you have the skin on. That being said, there are many cases, I fully agree, where you would like to avoid having the skin. So what we have done for some techniques, not for this one in particular, but for techniques which are creating truss networks, is you can also consider what happens along the surface to try to connect, in the case of trusses, beams that would be dangling otherwise, in such a way that you will not have these isolated islands. But yes, this requires a special treatment. I don't have the answer for the polyfoams we have. The main issue is that because you're cutting the structure, you might have parts which are completely disconnected from the rest, because the structures can create tips, right? They can create pointy cones inside, right? So if you cut that, you might have something dangling. So yes, that's a good point. And this needs to be investigated further. Mm-hmm. So should we take some other questions? I think.
I think there are only two questions left. One is about the applications medical.
Right. So yes, I think there's a lot of ongoing work in this particular space, and yes, for the design of shoe insoles as well. I mean, if you just do a quick search online, you will find a lot of interesting applications of that. So some of them are for sport, of course, like to try to get the best performance, and some of them are indeed for specific pathologies. Also for implants and things like that, right? Of course, it's a whole, I mean, that's not something we can do on our own, right? You have to team up with doctors and so on. We're starting to do that here a little bit. And it's I think it's a truly promising topic for this kind of approaches in the future.
Great. And then we have a last question, which is about what about several nozzles printing collaboratively?
Yeah, a great point. I mean, I think, yeah, this has been done a little bit, right? I mean, there's this is not something I looked deep into, but I'm sure, I mean, I have seen prior art dating quite some years back about this, right? So for sure, there are things that have been done. There are systems where you have multiple nozzles side by side, and people have looked into ways to exploit that. It's not something we have done a lot, but I think it's quite interesting as well. Independent nozzles would be great, right? And then collisions and path planning is probably interesting.
Yeah, there's a last comment about the ICE SL.
Ah, cool. Okay, well, excellent. We're happy to help you use it, right? So feel free to contact us, and especially for research and education, this is why we do it. So please go ahead. Excellent. Yeah, so I'm happy to exchange about it if you encounter any issue setting it up or anything like that.
All right, I think we're pretty much running out of time for this section. And then I would like to close this section. Thanks, Sylvain, to give us a nice talk and a lot of inspirational kind of discussion. And then look forward to have more collaborations and research in these areas.
Thank you very much, Charlie. And thanks to the organizers and to everyone for showing up, whether it's early or late, or I don't know for sure in your part of the world. Thank you.
Thanks, Sylvain. Nice.
Bye.
Bye. See you around.